Before I start with the talk, I actually want to introduce myself. So I'm a doctoral student at INRIA in Paris. I'm interested in automatic parallelization, data locality optimizations, and I've been working on compiler since about 5 years. So I started working on GCC, on Graphite, the Polyhedral optimizer, together with Sebastian. I've started to work on Poly, on LLVM a little bit. And another related project is the C-Lang Complete, which is C-Lang auto-completion plugin for Vim. And that's it. Then, most of the work at Poly, was funded by someone else. So I just wanted to mention the people who like paid my life and living, which I think was very nice and kind. And so I'd like to thank Welcome for the support for the travel here. And one of the interesting points is that there is some Google funding for the next 3 years. So I can work on that 3 more years. It won't die tomorrow. So what's our problem? Why are we doing Poly? So the problem is that life is really complicated. And that's a very broad problem, and probably too broad for a developer summit. So we want to focus a little bit more. So we say life for a programmer is complicated. And even this is a very broad topic. So let's see what Poly is about. So there are a lot of programmers are trying to focus on performance. They want fast programs, and especially for all those mobile systems, they want a low power consumption. And actually, we are really there was a lot of progress with this hardware. So we have vector instruction sets, we have caches, we have multicores, we have even dedicated vector accelerators. And this is a lot of cool hardware to get fast programs and use less energy. But the problem is, as more sophisticated the hardware is, the more difficult it is to actually get fast. You need to put a lot of effort and optimization effort to get a fast program. And so what I figured out is that this is becoming more complex, and at the same time, it's really, it's getting more difficult to solve the problem. Because as more optimization effort as you need to put in, as more performance, the programs become less performance portable. And that's an issue which I've seen is may become even more complicated if the number of architectures increases and becomes more diverse, which is going to happen with all those mobile platforms with the different vector accelerators. And so that's the problem we have. So the question is, how can we solve it? Or can this be solved? And I'm hoping we can solve this automatically. And now all of you will say, no, you can't. It's just automatic optimization doesn't work. You need human input. And most probably you're right. But I still believe there might be a subset of programs where actually we can make this work, and where we basically write one program and get a performance, can automatically generate fast code for that. And so my bet on this is Poly, and we try to solve a part of this problem. So what is Poly, or how does Poly work? So we just start with a very simple example, how to use Poly. So basically, you install Poly, which is very simple. You just put it into the LLVM source tree, compile it, and you get a shared object file. Then you load it into Clang or opt, which is basically just defining a shell alias, and your Clang and opt is Poly capable. And then it doesn't change anything. So your Clang will act as always. But you have the Poly flags available, so if you want to try it and try some Poly optimizations, you can. And so that's the first thing we want to do. We have a very simple program, a matrix multiply kernel. I love this kernel. I have it in every presentation. So, so if you want to get the best performance out of it, you use Clang -R3, and you get a reasonable performing program. And then you want to try, can Poly do anything useful? And it can. So if you use Poly and optimize it, basically you get I don't know how much it is, 6, 7x speed up, which is basically all cache locality. So matrix multiply, if you don't do loop locking, you don't get cache locality, and you don't get good performance. So with Poly you can get good performance for matrix multiply, which is a start. But probably you would say, hey, the problems I have are not matrix multiply. So can you do anything else than matrix multiply? And I was thinking, wow, I'm always putting matrix multiply on my slides, so maybe I cannot. So it would be cool if, like, I've seen some examples where I can do something else, and if you have an example where you think, hey, maybe that might be able, he might be able to optimize, you can just check it yourself. So what is necessary to realize if I can optimize your example? So the first thing is just to give you a little bit an overview what Poly is, how it works. So Poly is very simple. It's just an LLVM optimizer. So you take LLVM IR, you analyze it, figure out what you want to change, and change the stuff you want to change, and recreate LLVM IR. And so the way we do it is we analyze the LLVM IR, we extract the higher level information, the loop information, the memory access pattern, and create a polyhedral representation of this, which is some kind of abstract mathematical model. And based on that model, we can analyze it, do transformations. And if we are very, very basically lazy, we just create that model. And right ahead, we create LLVM IR from that polyhedral description. So that won't change anything at the performance of your program, but it at least shows we can analyze it and understand it. And then the next step is you want, hey, I installed Poly, I want some benefits. So sure, if you have time and if you want, you can put in the middle of that polyhedral representation, analyze it, figure out which transformations you want to perform, and perform the transformations. And basically by changing the polyhedral description of the program, you can affect the way the final regeneration of LLVM IR takes place. So we will have some examples how this exactly works a little bit later. And just to give you the general flow. So back to the problem of can Poly apply, like optimize my program? So the first thing you want to check is, can Poly understand my program? So that's very simple. You just use this poly minus show minus only option, limit it to the function you're interested in, and what you get is a CFG which highlights the parts of the program Poly can understand. So this is the CFG of the matrix multiply kernel. So as I've said, I can optimize matrix multiply. You see it's green, so Poly can basically recognize it, and later could apply some optimizations. In some cases, it might actually happen that Poly cannot optimize your program. So what to do about that? So the nice thing is, this, for example, is also a matrix multiply, which Poly cannot optimize. So Poly cannot even optimize all matrix multiply kernels. And the reasoning is that A, B, and C are actually pointers in C, which may alias. And if there is aliasing, it's difficult to reason about that problem. So Poly will give you an error message or just an information message to say, okay, there is some aliasing happening. We cannot optimize that program at the moment. So probably you want to fix it. So the easiest fix is just to define, okay, there is no aliasing, so we can optimize it. Or there are different options to solve it. We can, LLVM actually does a lot of inlining, so most of the time aliasing is not such a big issue because after inlining, it may disappear. Or we can improve the alias analysis, which is out of the scope of Poly, or we may add some runtime checks for aliasing. But the basic thing you should take from this is that in Poly you get these messages which tell you why a program cannot be optimized or analyzed by Poly. And if you think Poly should be able to analyze your program and it just cannot, I would be very glad if you drop me a line, write me an email or a bug report and complain, because maybe it should actually really be able to optimize the program. So the next thing is, after we detected the program, we want to understand what's the polyhedral representation. How does it look like? So the last year, I think I spent a reasonable amount of time of explaining how all the polyhedral stuff works. I won't this time. So basically, if you have a program, you have again another flag, polyrun export JScope, which basically exports the polyhedral representation. And it's really simple. You get for every statement, you get a domain and a schedule and a couple of memory accesses. The domain is basically the space of the loop iterations that will be executed in that kernel. So, for example, the first statement is surrounded by 2 loops, so we get 2 loop dimensions, and each loop dimension is limited by the loop bounds. And the schedule, yeah, basically maps each loop iteration to a point into the time. And so, for example, for this very simple example, the schedule just represents the original program. And so now we want to change the program a little. So we have, again, an even simpler program. We have a domain and we have a schedule. And the only way we optimize our programs is by changing the schedule. So here we want to do some loop interchange. So I apply a loop interchange, which is basically a mapping from basically switching the loop to loop dimensions. And as you see, if I modify the polyhedral representation, Poly will automatically generate the right LLVM. So if you want, I don't know, LVM does not have any loop interchange paths. So if anybody of you wants to go ahead and write a loop interchange path, it's probably applying this one line, switching of dimensions, and you can implement loop interchange, which I think is very nice and shows how powerful such a representation is. So we want to apply one more iteration, one more transformation, and this time we want to vectorize this code. So basically what we want to do is we want to create a loop which just has 4 loop iterations and which somehow is very close to some vector instruction. So what we do is some strip mining. Here the constraints are a little bit more difficult. We are introducing an additional dimension. And as you see, the code automatically generates an innermost loop, which has 4 elements, and it's, in this case, it's parallel. So some vectorizer, or like later in Poly, we could replace this by some vector instruction. Actually, that's the next thing we want to do. So I told you that you can optimize your program by changing the polyhedral representation. And you don't need to do anything else if you use Poly. Because Poly will take care of, it will automatically detect the parallelism. And so if you did the right transformations previously, if you did a good job here, and you exposed enough parallelism, Poly can just detect it, and either it generates calls to the OpenMP runtime and executes it on multiple cores, or if it's an innermost loop with a constant number of iterations that is parallel, Poly can automatically generate the right vector instructions. And that's just one example of another matrix multiply kernel. How changing the schedule can affect the transformations that Poly or LLVM is able to do. So we start with a with a normal program. Just you run clang -R3. We have GCC and ICC to compare the performance, and then we gradually modify the schedule to see how the performance increases. So basically, the only thing we do is to do some strip mining to expose this trivially vectorizable loop, and at that point, basically we do this. So we get a very small performance increase. And then we replace this trivially vectorizable loop by the actual vector instructions. And as you assume, if you replace a loop with 4 iterations with the relevant vector instructions, you get some performance increase. But the really interesting fact here is that basically this kernel has, in the innermost loop, it has a vector load, which is actually not a vector load, but it's some gathering of scalars and constructing a vector, which is very expensive. So during our previous scheduling transformations, we made sure that this innermost vector, this vector load, becomes loop invariant. So basically, the big speed up here is by the loop invariant code motion of LLVM. It's not Poly that does the big speed up. So now you may say, okay, so he's presenting some slide that LLVM is a good compiler, which is nice, but probably not the content of that talk. So what I want to say is, you don't need to implement all the fancy transformations inside Poly or somewhere else. You can really influence the performance of your program by modifying the schedule of by just modifying the polyhedral schedule. So LLVM is just able to do this loop invariant code motion because we created the right loop structure. We made sure that this load actually became loop invariant. And then LLVM does all this LLVM fiddling and figuring out what to do. But you can make LLVM capable of doing this by generating the right schedule. And so I think that's impressive. And so I'm not sure. How many of you are interested in working with polyhedral schedules and, I don't know, using them to optimize their programs? So there's a couple of guys. I think you're really brave. I think that's cool. But I think there are some other people who don't look too excited to implement the loop interchange with this polyhedral formula, which I didn't even explain properly. So yeah, I understand that. I'm actually, not all the time I'm glad to work on that. Sometimes I am, sometimes I'm, well, maybe not. But so there's at least a solution sometimes. So what we have in Poly is some automatic optimizer, which can take care of doing all the loop interchange and figuring out what to do. So basically, in Poly, we're just using Pluto. I'm not sure if all of, probably not. So Pluto is a polyhedral optimizer, which was developed, I think, in 2008. It got later then ported to the IBM XL compiler, and basically is the most successful polyhedral optimizer that does the interchange and the scheduling automatically. And so in Poly, we are able to use Pluto to figure out what schedule we want to have. And we have two optimizers. So we have POC, which is some kind of research project that includes Pluto and a lot of other stuff, which is very nice to play around with the polyhedral transformations. If you want to do research, you probably want to use POC because it has a lot of additional passes which you may take advantage of. It's also it's 3 years old, so it's major and it has good heuristics. But the problem is it's a research project. So it's a big piece of software which cannot actually be linked into Poly, but you need to call a binary, and you need to install it. So for the average user, he most probably doesn't want to install POC. So that's why we have ISL. So ISL is our polyhedral library, and fortunately, our polyhedral library now has the same algorithm implemented as Pluto, or not the same, but a very similar one. And so we can just use the ISL optimizer to get more or less the same results without any additional dependencies, without any additional requirements for the user to install anything. So that's actually what I think will be the production optimizer in Poly. So will be means it's not yet the production optimizer just because it's, I think it's recently introduced into Poly, so it's just not as mature and as tuned as the Pluto optimizer. So at the moment, if you want to get the fastest code, you probably use the Pluto optimizer. Anyway, we have two optimizers, so you don't need to work all the time with polyhedral schedules. I just told you about them because I thought maybe someone is interested. So then I like colorful pictures, so I got some performance numbers. So basically what we did is, this is a polybench, it's some kind of benchmark suites that contains computation kernels. So we have matrix multiply, obviously we have correlation covariance, Cholesky, some stencils. So just a couple of computation benchmarks. And we are fully automatically just using Clang minus O3 minus Poly to optimize that. And so as you see, we get some speedups. We also get some slowdowns, but it's actually interesting. This is all single thread performance. So the yellow one is without vectorization, and the green one is with vectorization. And you see, especially for the bigger data sizes, you can get 10x speedup just by doing some data locality optimizations, which I think is very nice. We also obviously got slowdowns. So basically, if you perform data locality optimizations, especially tiling, the source code you create is normally slightly more complicated. And there are some cases where there is just no data locality problem. There is just the problem fits into your cache. So it's just, you don't get any benefit by improving data locality even more. And so Poly doesn't have any heuristic to detect that cases yet, so that's why we get some slowdowns. And for the vectorization, we use a very, very basic vectorization heuristic. So basically what we see is in some cases we get really nice speedups with vectorization. And in some cases we don't. So the cases where we get nice speedups is most probably just because we are lucky that our heuristic matches. Or, yeah, in that case that it matches. But it definitely shows that Poly is able to do vectorization. And so now that's what I'm going to do in the next couple of months. I'm going to need to tune our heuristics to make sure that we actually, do the right thing. And I introduce vectorization when it's useful. And so we got also some parallel execution times. So this is with OpenMP parallelism on an 8-core system. And as you can see, for small problem sizes, you get 15x speedup on an 8-core system, which obviously is, again, data locality optimizations. And for the bigger problem sizes, you can get 80x speedup. So that's basically when you're just always flushing your caches without optimizations. So if you apply the right optimizations and keep everything in the cache, it's just you get an immense speedup. Obviously, that doesn't apply for all the programs. So some of the programs Poly was not able to recognize at the moment. For some of the programs, it just doesn't have any effect. But like there is a reasonable number of programs where I think Poly can give very nice speedups. And yeah, that's it. So looking at the current status of Poly, so what works? So all this green is like it works in terms of, I would say it's usable for experiments. So if you have your critical production software and you want to use Poly today, I would do some testing beforehand. It might work, but do some testing. Yeah, so we have this short vector instruction code generation support. We have OpenMP parallelization support. We have this still under construction item on the transformations. So that's basically representing our ISL optimizer, which works in many cases, but which still needs a lot of effort put into the heuristics and into the optimization model. And we have a planned one for OpenCL. So OpenCL basically stands for all the GPU code generation. That's what I wanted to use the last couple of minutes, is to look a little bit ahead. What's actually the bigger picture of Poly? So at the beginning, I told you like there are all those sophisticated hardware features which can be used. So for example, short vector instructions. Vectorization is actually, like there are a lot of compilers that already do very well with the vectorization. Like the ICC compiler can do some very good optimization, especially for inner loops. So there's some good existing work. For data locality and thread level parallelism, like existing compilers are not as good. So Pluto, for example, was able to show reasonable, significant speedups by just optimizing the C code that was put into ICC. So I'm normally comparing to ICC because comparing to Clang or to GCC is just like ICC normally beats those compilers in like performance or calculation intensive programs. So we've seen there's Pluto, which we are using in Poly. So I think Poly is in that area already doing a very good job. And so the last thing is about like this vector accelerators, GPU computation, which is I think a very interesting topic. But to be honest, I'm not sure. I think it's a very difficult topic. So I haven't seen any programs yet which do like automatic GPU code generation, like in a good way. So there is a lot of research going on, and then they have very nice results. But I think it's still, for me, it's a difficult problem. And the last thing, I haven't seen too much work targeting the overall problem. So basically, if you want to do vectorization, you can do some loop interchange before to expose more vectorization opportunities. But like especially like Pluto with this like advanced data locality optimizations, does like pretty complex loop transformations. And what I think would be very nice is if you can integrate the vectorization problem in the same optimizer so that you can use these complex loop transformations to really expose these trivially vectorizable loops such that you can not only vectorize a loop if it's obviously vectorizable, but that you can actually increase the amount of vector code you can generate. And so this is one of the things I'd like to target with Poly, and I think we have a very good infrastructure for that. And yeah, I must admit, I'm really not interested in inventing any new stuff. So I'd like to copy as much as I can. So as you have seen before, I just take Pluto. I don't. It's a really cool thing. So I don't spend any time on inventing something like Pluto. And so for this GPU code generation, there is some really good research going on. And actually, I think we at my group we're starting some collaboration with ARM to continue this work on GPU code generation. And so I hope that when the research continues in this area, we can just copy, steal, whatever, some parts for Poly, and yeah, target this overall problem. Because it's a really difficult problem, and I, by myself, I'm not convinced I can solve it, alone, at least. So if I can steal here and there, and maybe we can make some progress here. And yeah, so basically, what are my next steps? So the first thing is I want to make this core of Poly really production quality. So we want to have the ASL optimizer to be like well-tuned to make sure that you get very good single-thread performance. And you don't get like the slowdowns because there is a missing heuristic or something. And I want to make sure that we don't just have computation kernels, but that we actually can look at bigger programs. Like everybody is asking me, why don't you try spec? So it's just, most probably it doesn't work yet. So there is just, you need to spend some time to look into why it probably does not optimize certain cases. And I just want to spend the time to show that we can actually optimize bigger programs. And then there is this summarization point. So what I said earlier, I'd like to integrate the vectorization into the core optimizer such that, yeah, we can change the loop structure to actually expose more vectorization opportunities, which I think is still a very interesting topic. And then, yeah, GPU code generation. This was like stealing from the research projects and putting it into Poly. And so if there are any ideas, like if you think Poly is useful for you, or I don't know, you have a problem which you don't want to solve yourself and you want to offload your work, and you think it's something I might be able to do, I think because I'm stealing so much, I should also offer people to like offload some of their work to myself. So if you have any ideas, like please let me know. I'm very interested in that. And yeah, I think that's it. That's Poly, the current status of Poly. So thanks everybody for listening. If you have any questions, write a mail to the mailing list, or yeah, let me know right ahead. Thank you. Mm-hmm.
I have a question about your gen slide where you showed the big improvement. And the big improvement came from invariant improvement, right?
Yeah.
So did Poly reason about that, or was that
No.
impact of your vectorization?
So this is basically like we were still at the oh, first of all, I need to repeat the question. I remember this. So basically, I've shown this slide where we optimize the matrix multiply kernel and get an increase in performance. So the question was, did Poly reason about this? And the thing is, no, Poly did not reason. It didn't reason at all, because we are still and maybe I didn't emphasize that, but this is still the part where we're doing the transformation ourselves. So basically, I used this slide to show that if you do the right scheduling transformations, you can get good speedups. So basically, the improvement at that slide is you don't need to reason about LLVM. You don't need to reason about low-level details. You can focus on the core problem, and you can use the core problem to actually get significant performance changes. Mm-hmm.
ICC is slower than Poly. Did ICC fail to vectorize the matrix multiply?
Yeah, it did. Oh, actually, I think it did. It vectorized it, but it didn't do very well. So this is an It,
speed
it,
up is used, so
yeah.
it doesn't make sense if the ICC vectorizer should come on par with the
No, no, like this matrix multiply kernel is actually a very difficult one, like it's transpose matrix multiply. So basically there is no dimension where you can vectorize on, like there's just no good way to vectorize it. So basically that's why ICC, like normally ICC can optimize matrix multiply.
Is the example the same we showed on the slide?
No, it's, I think on the other slides this one is a different one.
Okay.
Because here you can vectorize on the j dimension, and like this is straightforward, and I assume ICC would get this one.
Yeah.
I don't, yeah, in that case it did not get it, because there is not a straightforward way to vectorize this.
I'm curious to know what is the test case you tried.
Oh, this one. Yeah, we can talk about this later. But yeah, just put 3 loops around this test case, and yeah. Mm-hmm.
So you mentioned that you want to spend more time on heuristics. And obviously, with this advanced framework, you have many possible optimizations. You have to trade off among them. These heuristics can become very, very complicated, right? So the alternative to that is doing some kind of auto-tuning calculation.
Yeah. Yeah, so basically I'm not interested into auto-tuning, but basically just because there's enough other stuff to do. But I think auto-tuning is a very interesting area, and like especially if you really want to get the most out of, like most performance out of it, it's probably yeah, the way to go. So there was some I think Lou and Noel Pouchet did a lot of work on this. So basically auto-tuning for polyhedral optimizations is a difficult problem, just because the schedule you can choose is like you have unlimited, the optimization space is just immense, you cannot handle it. But he showed that just if you restrict yourself to a very limited subset of the scheduling space, you can already achieve very, very good results. Mm-hmm.
Doesn't it seem like auto-tuning is like doing a search space, right?
Yeah.
So wouldn't it make more sense to do a semi-guided approach where you're using the polyhedral representation to do your schedule and then giving information from the source up to then be able to tune it, so semi-automatic. Because if you're doing auto-tuning, it's like you have to search through the whole space, you're trying all these massive number of combinations of parameters to the loop transformations, right? So doesn't it make more sense to do a semi-guided approach?
Yeah, so the question was if it makes more sense, instead of doing auto-tuning, to take a guided approach and ask for information from the programmer to optimize the program.
Or a tool,
Or a tool. Yeah, I think it's a reasonable approach, sure. If there is a programmer has like, especially if he has domain-specific knowledge about the problem, and he can pass this to the compiler, I think it's yeah, a very helpful thing probably to do.
So the big picture about poly, I saw, yeah, so dependence analysis. Is there dependence analysis inside Pluto also? In order to do those transformations?
That
Unit extra analysis.
So it depends what you think is Pluto. So Pluto as a binary, as a tool, has obviously a dependency analysis. I use Pluto as some kind of library where I basically use just the scheduling optimizer, which takes as an input dependencies, and I calculate the dependencies myself. Just because the dependency analysis in Pluto is, well, first of all, because Poly needs a dependency analysis anyway to find out if some loops are parallel or something like this. And the second thing is that the dependency analysis in Pluto is not as expressive as the whole Poly infrastructure. So we have, like, I'm not sure.
Okay, so let me rephrase. So I'm saying that dependence analysis fit into the Pluto in some way or not?
Yeah, we're calculating dependencies, and like the Pluto algorithm basically takes in the domains and a set of dependencies and returns the optimal schedule.
So if you get better analysis, you get better results from Pluto, right?
Sure, if you can do a better dependency analysis, you can get better results, yeah.
Okay.
Can you represent like parametrical bounds in Poly?
Yeah.
So in the case, if you want to do some transformation, would you better that you
The question was if we have parameter, like if we have parametric loop bounds in Poly, and if we do some code versioning based on those parameters on the size. No, currently so Poly itself does not do any versioning at the moment. That's one of the reasons why we get some performance regressions, which is definitely like needed and necessary. And during code generation, our code generator itself does versioning, but not. Basically, the reason it does versioning is it's optimizing extensively for reduced control flow. So basically, if you check some constraints, like if a parameter is positive, you can simplify the loop nest. So that's done. Okay, so I think that's all. Thanks a lot for coming, and have a good time here.